All right, good morning. Happy Wednesday. Doesn't quite feel like a Wednesday, but it is. All right, so the plan for today is if we don't finish chapter 3, we will be really close. Okay, and then on Thursday, tomorrow, we'll start chapter 4. The homework for this week and the quiz for this week goes up through chapter 3. So pretty much by the end of today, you should have everything you need to complete that. Make sure you sign in for attendance. Homework, again, just as a reminder, is for practice. Learn the material, take your time, figure things out. If you want to work with other people in the class, please do, but work together, make sure you understand the material. And then the quiz is really designed for you to test yourself. So take advantage of those 3 tries. And certainly on the first one, try to take it without any resources and take it like a test and just see how you do. If you don't do so well, that means that you need to study a little bit more. Make sure you realize you can see the correct answers. You have to go up. There's a drop-down menu toward the top right. I think it says My Answer, and if you click the drop-down, it says Reveal Answer or something like that. And you can see the correct answer on the ones you missed. So study it, figure it out, and then you can take the quiz again, and you could take it a 3rd time if you need it as well, okay? So, you have to test yourself every week just to make sure you're keeping up with the course. There's also, and a lot of students have liked this, an adaptive quiz that kind of takes you through and tries to figure out what you need to work on. That's just for practice, so use that for yourself if you like doing that. I've gone through and done some of them, and it seems like a pretty good way to check yourself as well. Question? So I will start updating grades in Blackboard, because the grade book in there doesn't allow me to change anything. I could contact their tech support and ask them to do the highest quiz, but I'd have to do that each week. And so what I'll do is starting probably early next week, I'll start uploading your grades into Blackboard, and I'll just upload your highest quiz. So your highest quiz 1, your highest quiz 2, and so on. And then I'll keep running grades for the semester in Blackboard. Your Achieve quiz score will be messed up. Okay, so be aware of that your Achieve quiz score will not be right in Achieve, but I will get it right in Blackboard, okay? Don't forget about office hours, good way to get a free percentage added to your grade for the semester, plus a good way to hopefully learn the material. All right, we started talking about isotopes last time. So what did the scientist say when he saw 2 helium isotopes? Oh, that's sad, but all right. It's chemistry humor, come on. All right. Okay, any questions before we start? Everybody's semester going well? Is it nice to be back in person? I still haven't gotten used to it. It just doesn't feel right for some reason. I taught 2.5 semesters on Zoom, so it's like, wow, I actually get to be back in class again, so it's kind of cool. All right, so look up at the top of the screen here. Those are 3 isotopes of carbon, okay? You don't have to know, I'm not gonna ask you a question that says, tell me all the isotopes of tin. If you could do that, I'd be impressed. I think tin has like 10. But I will list them for you. You need to know what the definition of an isotope is, and you need to know how to count protons, neutrons, and electrons. But these are the 3 isotopes of carbon. Remember, it's the protons that identify the element, and that's the bottom number, the subscript. That's the atomic number. Okay, so this number, oops, that didn't quite work. Okay, so that bottom subscript, atomic number, number of protons. Also for a neutral atom, it happens to be the number of electrons because they have equal and opposite charge, protons and electrons, and then that would be neutral. The top number, what's the top number called? Yeah, the mass number. And most of the mass of the atom, protons and neutrons, okay? So if you want to get the number of neutrons, you're just going to subtract, in this case, 12 minus 6, okay? Mass number minus the number of protons will give you the number of neutrons, okay? And as we went through last time, for carbon-13, we end up with 7 neutrons, 13 minus 6. For carbon-14, we end up with 8 neutrons, 14 minus 6, and that's the difference between isotopes, okay? They're going to have the same chemical properties, although you might find some differences. For example, carbon-14 happens to be radioactive. That's an unstable nucleus. We're not going to do much with nuclear stuff in this course, but that's an unstable nucleus for carbon-14, and it will kick something out of the nucleus to reach a stable nucleus. All right, what else do we have up on the screen? This is a schematic, of a mass spectrometer. Okay, so if you happen to go on in chemistry, which probably not a lot of you will, because a lot of you are in dental hygiene, and nursing, and forestry, and nutrition. Am I missing anyone? Yeah, who am I missing? What's your area? Okay, speech language pathology, thank you. So anyway, you've kind of picked what areas you want to go into, but if you go on in chemistry, we have a number of mass spectrometers in the building for our upper division teaching labs and also for research. And what this instrument allows you to do is separate things by mass, okay? You can also fragment things first. So you could have a big molecule, you hit it with an ionization source. This one says it's an electron beam. That's a pretty wimpy ionization source. You can hit it with much stronger ionization sources like a plasma, and you can really fragment things. But anyway, you create different size things by mass. They are charged, and you can separate them by their charge to mass ratio. Okay, so essentially the lighter particles will deflect more in the magnetic field, the heavier particles will deflect less, and you separate things by mass. And so the first mass spectrometer, which I think was invented in like 1920, somewhere in the 1920s, was used to determine isotopes. And the first one was neon. Neon was easy, it was already in the gas phase. So neon is one of the noble gases. It's atomic number 10 up on your periodic table. So neon already is a gas, easy to separate with the new mass spectrometer in 1920. And you end up getting, and it doesn't show you this here, but let me just do a quick drawing here. So this is a mass of about 20, and then the other isotope 21, the other isotope 22. You will get peaks, and the area under the peak is proportional to the percentage of that particular isotope, okay? So the most abundant isotope is neon 20, so the peak here would be quite large. Neon 21 is only 0.27%, so that would be really tiny. And then the other one at 9.25% would be a little bit larger. Now, I'm sure I didn't draw that to correct areas, but you get the idea. Okay? Yes?
So I have a question. Like, how would you find the natural abundance in that chart, like when you do the math for it?
Well, for what we're going to do, I would have to give you the natural abundance. Okay. Now, theoretically, if we were more, if you were in an upper division lab, you would actually run this spectrum. You would collect the data. Of course, the computer would integrate the area under the peak and give you that, would give you that data.
Oh, I see. Thank you.
Okay, but for what we're going to do, and we're going to do some problems today, so you're going to get to do some math here in a little bit to figure out average atomic mass for these isotopes. I will give you that data. All right? Okay. But I just wanted to show you the experimental part of this, that if you wanted to get the abundance of each isotope, you would use a mass spectrometer. Okay, so let's look at the periodic table. Can everybody see on neon? What do you see underneath the symbol? What number do you see? What's that? The mass, and what is it? Okay. So that mass that's underneath is what we call, and we'll do more with this today, is an average atomic mass. Okay, so I just want to introduce that now since we have this up on the screen. We're going to do a few more things and we're going to come back and figure out how to calculate this. But one thing you'll notice is that neon 20 is the most abundant. It's 90% of any neon sample. All right? So it shouldn't surprise you that the average atomic mass is closest to 20. Okay? Now, we do have 21 and 22, so we expect it to be higher than 20, and in fact, it's about 20.2, so that kind of looks right. We're going to look later at how to calculate that. Okay, but just for now, keep in mind that's an average mass of all the isotopes of that particular substance. All right, let's look a little bit closer. We've already done this in terms of writing atomic number and mass number. So just to review, atomic number is a subscript, mass number is a superscript. And we've already done that. Protons for the atomic number, mass number, most of the mass of the atom is protons and neutrons. Electrons do contribute a little bit of mass, but not much. Okay? So the main isotope, the most abundant isotope of helium, is helium-4. Okay? And when we talk about isotopes, if I identify that isotope and say that's helium-4, what I'm saying is the mass number. Okay? Helium-3 also exists, okay, which would be a different number of neutrons, only one neutron compared to two. So, so if I say carbon-12, carbon-13, carbon-14, or in this case helium-4, I'm referring to the mass number. Okay? I don't need to refer to the atomic number, right? No, because if I say helium, you know the atomic number. Don't have to have it memorized, but you can find it very easily. Just look at your periodic table. All right, so when you look at the periodic table, again, remember that number at the bottom is an average mass. Okay, it's not any one particular isotope. All right, so take a minute here and write out this particular isotope that has 92 protons, as any uranium isotope would have, and 143 neutrons. Okay, so use the proper designation, atomic number as a subscript on the left, mass number as a superscript on the left. So the atomic number is easy. Just need to do the mass number. Are we good? Do we have a mass number? What'd you get? 235. Okay, so just add up your protons and neutrons, 92 and 143, and this particular isotope of uranium is uranium-235. It's not a particularly abundant isotope. Uranium-238 is much more abundant. Okay, that's another isotope of uranium. All right. Any questions on writing out those symbols? Yes.
So when we subtract 92, or I'm sorry, add 92 plus 143, like how did we get 143? Because I know that's neutrons, but like how did we find that?
You were, so again, you would have to be told that a particular isotope of uranium happens to have 143 neutrons, as I did in this problem. Or I could turn it around and give you uranium-235, and then ask you how many neutrons are in uranium-235.
Okay, so how are we able to find that?
Just look at the atomic number, which might be given, or you might have to look at the periodic table and see that it's 92 for uranium. So find uranium down at the the bottom row, okay, and you'll see a 92. You would then take 235 minus 92, which would give you, so in this case, if I gave you this on an exam and said how many protons, neutrons, electrons, for example, okay, the first thing you would need to do is look at your periodic table and find atomic number 92. So that would tell me 92 protons, neutral 92 electrons to balance those protons. And then I would have to take 235 minus 92 to come up with 143 neutrons.
Okay, I see. Thank you.
All right. Oop, here we go. Oh, it's so fun. All right. Okay, and as I already pointed out, make sure you realize that's average of the isotopes, that bottom average atomic mass. All right, so let's look at actually how we calculate this average atomic mass, okay? And it's what we call a weighted average because each of the isotopes is going to have a different abundance. But let's compare that to what we typically call kind of an average, what's really the mean, or an equal average, all right? So these, I guess, are supposed to be poker chips. We have some $1 poker chips and some $2 ones. Since we have equal numbers of those, you can probably just look at that. And what we just normally say, what is the average value of those 8 poker chips? Somebody said it. Where was that? How much? 1.5, right? So that's easy, right? We can either just look and say, oh, well, we have the same number of $2 chips as $1 chips. The average, or what really is the mean, is going to be right in the middle, okay? So our average is going to be $1.50, essentially, okay? Now, let me show you a different way we could calculate it. So normally, this one we can just look at, right? Or we'd add up 1 plus 1 plus 1 plus 1, and we'd get 4. We'd add up the 2s, that would be 8. So we have 12 total dollars. And there's 8 chips. So normally, if we were to calculate this, we would take, is everybody with me? Do the math, add up all the $2 chips, we get $8. The $1 chips, we get $4. We have $12 total. We divide by 8 chips total, and we get $1.50. Okay? Now, another way, let me show you another way that we could calculate that. I could do this. I wish I had a little bit more room. Let's see if the blue shows up on the green. That's not too bad. What do you think about that? 0.5 times 1 plus 0.5 times 2. Now, normally we wouldn't do it this way, but we could. What does that work out to be? Same thing, 1.5. So what I'm saying in that calculation, 50% of my chips are $1 chips, 50% are $2. Okay, so I do have to convert the percentage to a decimal by dividing by 100. Otherwise, I'm going to get a number that's 100 times too large, because to get to percentage, we multiply by 100. But this is a way I could calculate the mean. 50% $1 chips, 50% $2 chips, and I'm going to end up with that same 1.5. With me? All right, now let's change it up where this might more represent, how did that happen? An isotopic abundance, where one isotope is 90% of the sample and the other isotope is only 10% of the sample. How would we calculate that? Now, we could, if we actually had the values and the numbers of each, we could add them up. But the typical way we're going to do it is like I did just up there. Okay, we're going to go, let's see if they, but we're going to go, and we'll see this on the next slide, we're going to do the calculation. We're going to go 0.1, 10% of our chips have the value 1, and 90% of our chips have the value of 2. And check that on your calculator. Punch that in your calculator really quickly. So we have 10 chips total, 10% $1, 90% $2. You should get 1.9. Double check that really quick for me. Are we good? Okay, and that's what we call a weighted average, and that's how all these isotopic average atomic masses are going to be calculated. They are weighted averages. Okay, we don't have equal percentages of each isotope. Okay, so here's the calculation. That's just on a different slide. I already did it. Okay. So any questions on the setup there? Okay, so this is not the mean. This is what's called a weighted average. A mean is a type of average, but this is a weighted average based on percentage of each component. Okay, so do a quick calculation here for me. Now, before we even do this, okay, we could look at the periodic table, but don't look at the periodic table yet. But look at the abundances. Most of carbon is carbon-12, almost 99%. So we expect, even before we do this calculation, this should come out very close to 12, okay? Only about 1% carbon-13. There's actually carbon-14, as we talked about, but it's like 0.00001%. So they didn't even bother to put that in this calculation. So do a weighted average for me, and then we'll work this out. So go ahead and, if you want to talk to your neighbor or you just want to sit there, see if you can set up this calculation. Let me know if you have questions. One reminder, don't forget to divide your percentages by 100 to get a decimal. Okay, you want a decimal times each of those masses. How do you stay amused? How does that look to everybody? Look all right? So again, weighted average, most of the mass of an average sample of carbon is going to come from carbon-12. It's about 99% of that sample is going to be carbon-12. Only a little over 1% carbon-13. As when we do our calculation here, we should end up very close to about an average of 12. And I was perfect. I wrote right over top. Oh my gosh, it's like I planned that without even knowing what I was doing. It's kind of a mess. So let's back up so you can actually, everybody good with that setup before I cover it up here? And we get about 12.01. And if you're thinking about sig figs, I'm not even sure we'd have that many because the 1.07 really only has 3, but we'll worry about sig figs later at this point. So we look at the periodic table, there's an extra sig fig, but you see 12.011. Okay, that's our average atomic mass. Okay, any questions on that calculation? Yes?
On the quiz, it was giving us like the same type of problems, and it was saying that it was 3 sig figs, so if you didn't put
3, it marked you wrong. Okay, why? It does that on some problems. It specifies you have to input with a certain number of sig figs, so watch that. There's not many like that, but watch for that. It does do that sometimes. Okay. One thing to point out here, and this is not going to be a main emphasis for us, by definition, carbon-12 is an exact mass. The mass of carbon-12, by definition, is exactly 12 AMUs, or 12 atomic mass units, also just abbreviated U. All the other masses are based relative to that. And if you remember, the mass of a proton is not exactly 1 AMU. The mass of a neutron is not exactly 1 AMU. So none of the other masses are exact. They're going to be very close. So carbon-13 is approximately 13. Carbon-14 is going to be approximately 14, but you will see little differences, and that has to do with the mass of a proton and neutron not being exactly 1 AMU. Okay, here's another problem that I just made up. So let's go through this. So that last example, 99% roughly was carbon-12. Our average atomic mass turned out to be very close to 12, as you'd expect. So if you look at the periodic table, and you see 12, you go, oh yeah, the most common isotope must be carbon-12. Okay, it's right at 12, it must be carbon-12. Well, let's try another one. Look at bromine. What is the average atomic mass of bromine on the periodic table? What do you see? Whether you have the periodic table in front of you or you're looking at one in the room. What do you see? Okay. Okay, that's easy. We just look at a periodic table. Easy question. Okay, or depending on how many sig figs, maybe 79.90. So here's a question for you, and I want you to turn to your neighbor and try to make a decision here. Does this mean that bromine 80 is the most abundant isotope? Turn to your neighbor. Yes or no? Does this mean that bromine 80 is the most abundant isotope? Yes or no?
like, is carbon 12? Or is it like our molecule?
So try to think like I think, since I came up with this question. All right. Seems like you had some good discussion going on. So is bromine 80 the most abundant isotope? Yes or no?
Not necessarily.
Okay, I have yes, I have not necessarily.
Well, since it's weighted, it's going to be pulled to whatever is the largest, and that's why I think it's
Okay. Any other thoughts, ideas? Yes.
The equal parts, 81 and 79, is leading to a number around 80 each.
Okay.
Knowing with this little information.
Yeah. Good observation. I like that. So remember, this is an average mass. Okay. So for a lot of the elements, not all of them, for a lot of them, the average mass will end up being close to, you look at carbon 12.011, yes, the most abundant isotope's carbon 12. You look at nitrogen, it's almost 14. Yes, the most abundant isotope of nitrogen is 14. Oxygen is almost 16, 15.999. Yes, the most abundant isotope of oxygen is 16. Okay, so that will work in a lot of cases, but it does not work for all elements. Okay, so the point of this is that, remember, this is an average atomic mass that you're reading. Okay, and it does turn out, and you were exactly right, that bromine is about 50% bromine 79 and about 50% bromine 81. It's actually 51 and 49. Okay, so now do the calculation for me. Calculate your weighted average and get the average atomic mass of bromine. Okay, now I don't expect you to know that. I don't expect you to memorize isotopes and abundances and all that, but I do want you to know that that number you're reading is an average, so it's not necessarily the most abundant isotope. And then just assume, I guess I should say, assume bromine 79. Its mass won't be exactly 79, but use 79. It's going to be very close to 79. Bromine 81 is going to be very close to 81. So just use the rounded numbers. Oops. And we really only have 2 sig figs since I didn't give you extra digits in the mass, but carry some extra digits there. What'd you come up with? 79.9. Did it come out 9.8? And that's probably because I just rounded my numbers. Just double check here. Okay. So I did a little rounding in my calculation. So the mass of bromine 79 is going to be exactly 79. The mass of bromine 81 is not exactly 81, and I probably rounded my percentages a little bit to make it easier. Okay, but you get the idea. Okay. Any questions on this one? Okay, so the key point there is, and let's just to repeat, that mass you read typically below the element is an average atomic mass. A lot of times it will tell you the most abundant isotope, but not always. Yes?
How did we get 81 as a mass again? So is it like between 80 and 81 in bromine?
Well, the bromine 80 isotope really doesn't exist, okay? So these are the two main isotopes of bromine, bromine 79 and bromine 81. You don't need to know that,
Oh, okay, thank you.
okay? That would be something on an exam, I would give you that information,
Sounds good.
okay? But what you do need to know is that, we look at bromine and we see a mass close to 80. That does not necessarily mean that bromine 80 is our most abundant isotope, and in fact, in this case, it does not. Okay, so just be careful. A lot of times that will work, in other cases it will not. All right, let's do a little summary here. Protons identify the element. So if we're looking at bromine, you see an atomic number of 35. Every bromine isotope has 35 protons. Every atom, every ion, every isotope of bromine, 35 protons. Okay? Mass number, as we already talked about, protons and neutrons, that's most the mass of the atom. Isotopes have different numbers of neutrons. Of course, they have the same number of protons to be isotopes of the same element. So bromine 79, bromine 81, they both have 35 protons. Okay, so let's just write those out real quick, just since we just did that. Okay. Okay, it's not bromine if it doesn't have 35 protons. Okay, now of course these will have different numbers of neutrons. You can do the math. What do we get? 44 for bromine 79, is that right? Did I do that math right? Versus 46 neutrons for bromine 81. Okay, so it's a difference in number of neutrons. Okay, so make sure you know how to write what we call an isotopic symbol. Okay, that name should make sense to you. So when we write helium or any element with the atomic number at the bottom, mass number at the top, we call that an isotopic symbol because we could differentiate our isotopes just like we did with bromine 79 and bromine 81. And again, one last time, just to reemphasize, when you look at a periodic table, so here's platinum. Platinum is in a transition metal. It's in the third row of transition metals, so come down element 78, atomic number 78, right by gold. All right, so platinum's quite a valuable metal as well. That does not tell us the isotopes. Okay, so that does not tell us the isotopes of platinum. It's telling us this is the average of the isotopes of platinum, the average mass. All right, a little bit more for today. We have about 11 more minutes. We're going to get into starting to look at reactions in a sense because reactions are going to involve electrons. Okay, so chemical reactions involve electrons. We're going to find out it could be something losing electrons, something gaining electrons, sharing of electrons between atoms, but it involves electrons. Chemical reactions involve electrons. So this would actually represent helium, because if you want to count here, 2 protons, 2 neutrons, 2 electrons. Okay, so 2 protons, atomic number of 2, that's helium. If we wanted to go further, we could write this particular isotope, 2 protons, mass number of 4. 2 protons, 2 neutrons, mass number of 4. Okay, so let's do a little bit of review before we actually start getting into electrons and gaining, losing electrons. Don't forget that all of this kind of built on itself, right? There was more before Dalton, but Dalton really pulled it all together into a unifying atomic theory. He was the first to really, not the first to propose atoms, but the first to really write it down into a cohesive theory. Atoms are indivisible particles. Turned out not to be quite true. because electrons were discovered first. And then Thomson proposed the plum pudding model, where these electrons are embedded in a positive cloud or matrix spread out throughout this positive sphere, like raisins in plum pudding. Then Rutherford comes along, discovers the nucleus. Okay, so that positive charge is not spread out over the whole atom. It's actually very, very, very concentrated. Positive nucleus, very small, very dense in terms of mass. Mass and volume, of course, but very dense positive nucleus. So we learn more about the atom. Okay, and this was the Rutherford experiment, bombarding a very thin gold foil with alpha particles, a radioactive particle. Let me actually show you what an alpha particle is now that we know isotopic symbols. So an alpha particle just happens to be equivalent to a helium nucleus. It doesn't have the electrons, but it just has the 2 protons, 2 neutrons. Okay? So some radioactive substances, to stabilize that nucleus, they kick out an alpha particle. They kick out 2 protons and 2 neutrons in the hopes to get to a nucleus that is stable. Okay, so that is an alpha particle. We typically don't write it with the element symbol. Okay, so you'll typically see alpha particle written with the Greek letter alpha, just like that. Okay, so 2 protons, 2 neutrons. So those are kicked out of some radioactive nuclei, and he used those, and most of them went right through the gold foil, undeflected. A few deflected at large angles to indicate this very small, dense, positive nucleus. For now, we're not going to talk much about the Bohr model, but Bohr then came along and said, well, let's imagine the electrons orbiting the nucleus, kind of like planets orbit around the sun, all right? And that there's only certain allowed orbits. The electron cannot just exist anywhere. There's only certain allowed orbits. Okay? We'll come back to this later in the book. And then, this really got going in kind of the mid-1920s, this whole quantum model. The electron is so tiny, it doesn't behave like a classical particle. And I know probably a lot of you haven't had physics, but we talk about classical mechanics, where we talk about real-world particles and how they behave. Well, these really tiny particles like an electron do not behave like particles in the real world do. And so electrons actually have particle-like properties at times, but they also have wave-like properties at times. And it limits how much we can know about the energy of the electron and its position. Okay? So if you've had a little bit of chemistry, you've probably heard of this concept of an orbital. Has everybody heard about orbitals? That it's not an orbit, it's a region of space where the electron is most likely to be. Okay, so we think about these boundaries. Well, most often the electron will be in this region of space, and that's what we call an orbital. And so that's where the quantum model goes beyond Bohr's more simple model of orbits. All right, so last thing for today, and I think this is the last thing for the chapter. Pre-lecture, you should have done a little bit with ions, so you should be familiar with this. Key concept. Don't change the nucleus in a chemical reaction. The atom stays the same. Remember, way back to Dalton, atoms are neither created nor destroyed in a chemical reaction. Okay? That means the protons cannot change. The nucleus doesn't change in a chemical reaction. What's changing is the electrons. Okay? So ions, just by definition, have a charge, which means we're going to have different numbers of protons and electrons. Remember, protons and electrons are equal and opposite in charge. If we have a charge, we have a different number of protons and electrons. And it's always the electrons that change. So lithium, look at your periodic table. You will see an atomic number of 3, if it'll let me write here. Okay, so lithium atomic number of 3, 3 protons, 3 electrons, neutral atom. Okay, we're going to talk about typical ions that form in reactions, but the alkali metals, that first group of the table, will tend to lose 1 electron when they react. So one of these electrons goes away. Actually, it's given to something else. Something else takes that electron. And so now we have 3 protons still in the nucleus. The nucleus doesn't change. We now only have 2 electrons. So our charge is, as you can see on the screen, +1. Okay? Piece of cake, right? It's just difference between protons and electrons. 3 protons, we lose 1 of the 3 electrons, we're now down to 2. We now have a +1 charge. And we would write that, we just simply write lithium with a plus sign. Okay, if it's +1, we don't have to put a 1. If it's 2 or 3 or 4, we're going to have to put the number. But just for a +1 ion, we just put plus. Okay? What we're also going to find is that metals will tend to lose electrons when they react. Metals will tend to lose electrons. Non-metals will tend to gain electrons. So here's fluorine. Find fluorine on your periodic table. Atomic number of 9. 9 protons, 9 electrons, neutral atom. The halogens, when they react, will tend to want to gain 1 electron. We'll talk more why that's the case as we go on, so hang with me. We can't answer all the questions at once. But we're going to add 1 electron. Okay, so say lithium lost its electron and gives it to fluorine. Okay, so fluorine's going to gain an electron here. Electron going to come in. We now have 10 electrons. 1 more electron than proton, -1 charge. And I just wrote over that. That didn't quite work. Okay? Not so bad, right? Let's do a couple more if we have like 2 more minutes. All right. Do this one for me. Atomic number of sulfur is 16. Find that on the periodic table. Sulfur commonly forms what we call sulfide ions. So for the nonmetals, when they gain electrons, we change the ending to IDE. So watch for that. Oxygen becomes oxide. Fluorine becomes fluoride. Sulfur becomes sulfide when it becomes a negative ion. Okay? So how many electrons in sulfide? 18. 16 protons. With a -2 charge, we must have 2 more electrons. Okay? Piece of cake. All right, let's see if there's anything else for today. All right, we don't need to do that. Okay. So again, remember neutral, same number of protons, electrons, ions. That's it. All right, I'm done a minute early. Woo! All right, let me know if you have any questions. Come on down. We will get into chapter 4 tomorrow. Again, the homework and the quiz goes up through chapter 3, so you should be good. Get started early, get it done. Make sure you give yourselves enough time to do the quiz 3 times if needed. You don't have to do the quiz 3 times, but your best score counts. Okay? Oh, attendance, we good? Everybody? Attendance? All right. Have a great day. Enjoy the sunshine. Hi.